When a fungus lands on the right ant, the ant becomes a plant. The animal you are looking at is a carpenter ant. She is hanging from the underside of a leaf 26 centimeters above the rainforest floor. Her mandibles are locked into the leaf's main vein and will not release. A thin, pale stalk is growing out of the back of her head. She has been alive for about 10 more minutes than you might think. There are two stories happening inside this ant's body right now. We are going to follow both of them. A few weeks ago, this ant was foraging on a fallen log in the rainforest understory of Thailand. She is a member of Camponotus leonardi, a tropical carpenter ant species. Her colony has about 1,000 sisters in it. They live in tunnels carved out of dead wood somewhere overhead in the high canopy. She is, by any reasonable measure, a successful animal. She is built to walk for hours along scent trails laid down by other workers. She finds food, she brings it back, she defends the colony from intruders. She has been doing this every day for several months, about 3/4 of her expected adult lifespan. She has good eyes for an ant. She has working antennae that can detect chemicals at concentrations a human cannot match with any handheld instrument. She is, in the way most of her colony mates are, an excellent processing unit for the colony's collective survival. She is also breathing. Carpenter ants breathe through small openings on the side of their body called spiracles. Air enters, air leaves. She has been breathing without thinking about it for her entire life. This is about to stop being a casual activity. A few weeks ago, on the underside of a leaf about 3 meters away from her, a pale stalk was sticking out of the back of another carpenter ant's corpse. The corpse had been there for weeks. The stalk had been growing through it for days. At the top of the stalk, a flask-shaped fruiting body was producing thousands of microscopic spores per hour. The spores fell, slowly, in a downward column toward the forest floor. Most landed on dead leaves, some landed on damp soil, a few landed on other species of insects that they could not infect. 3 landed on a different carpenter ant of the same species, but lacked the chemistry to take hold. 1 spore landed on the body of the ant we have been following. It was so small that she did not detect it. It was so small that it did not weigh anything she could measure with her senses. The spore is Ophiocordyceps unilateralis. It does not have a brain. It has chemistry. She did not notice the spore land. She also did not notice when the spore began secreting enzymes that dissolved her exoskeleton at the contact point. Carpenter ant cuticle is made of chitin. The enzymes broke it down quietly, locally, in a spot the size of a single ant pore. She finished her foraging trip. She returned to the colony. She went out the next morning to walk her usual scent trail. She continued to feed the colony. She continued to be fed by the colony. There was nothing visibly wrong with her. There was nothing chemically wrong with her as far as her sisters could tell. Her sisters cannot tell. This is important. Once the spore was inside the ant's body cavity, it stopped being a spore. It started being a fungus. The fungus does not at first behave dramatically. It begins by feeding on the ant's fat body, an organ insects use roughly the way mammals use the liver. It is non-essential to short-term survival. The ants can lose substantial fat body tissue and continue to function. The fungus grows. It branches. It spreads through the body cavity in long thread-like cells called hyphae. It does this for about a week without doing anything else. It is not, during this period, trying to be detected. It is acquiring resources. The ant feels normal. The fungus is sizing up the building. Days 7 through 12. She is still foraging. She still recognizes her colony's chemical signature. She still takes food from the foragers who return ahead of her. She still gives food to the foragers behind her. There is now visible biological activity inside her body. Researchers at Pennsylvania State University, using fluorescent microscopy, have documented that by this stage, fungal cells are forming a 3-dimensional network throughout her muscles. They wrap her mandible muscles, they wrap her leg muscles, they wrap her thorax muscles. But, and this is the part that surprised the researchers when they confirmed it, they do not enter her brain. Her brain is still her brain. Her thoughts, to the degree an ant can have thoughts, are still her thoughts. The fungus is not invading her mind. It is invading her body and leaving the operator alone, for now. The fungus has assembled an infrastructure. Each muscle bundle in the ant's body is now surrounded by a sleeve of fungal cells that can physically interfere with muscle contraction. The mechanism is chemical. The fungus releases compounds that directly disrupt the sarcomere, the basic contractile unit inside every muscle fiber. The Penn State research describes this as the fungus building a tubular scaffolding within and around the ant's muscle bundles. It does not invade the brain because it does not need to. The brain sends signals, the muscles execute. If the fungus owns the muscles, it owns the output. The brain is just a sender, and the receiver has been hijacked. This is, biologically, a significantly more elegant strategy than the zombie framing implies. The fungus has not turned the ant into a zombie, it has turned the ant into a remote-controlled vehicle. The driver is still inside, the driver still wants to live. The driver no longer has the controls. Around day 14 or 15, she begins to behave strangely. She wanders off her foraging trail. She does not know why she is wandering off her foraging trail. She tries to walk back. Her legs do not return her to the trail. They take her in a different direction. She climbs. Carpenter ants do climb in their normal lives, to and from the canopy nest. But this is different. She climbs at the wrong time of day. She climbs to the wrong type of plant. Small understory vegetation, not the trees her colony lives in. She is trying to fight it. From the inside, she is doing what an ant does when its body misbehaves. She sends contradicting signals from her brain to her legs. None of them reach the legs. She arrives at the underside of a small green leaf. The fungus is doing very specific work right now. It is steering the ant to a precise location. Studies in Thai rainforests have documented that infected carpenter ants are positioned with significant statistical regularity at approximately 26 centimeters above the forest floor on the northern side of the plant in humidity of 94 to 95% in temperatures between 20 and 30 Celsius. These are the conditions under which the fungus reproduces most successfully. The ant is being placed in a microhabitat the fungus needs. The fungus is not aware of compass direction, height, or humidity as concepts. It is using a chemical thermostat, a set of growth and behavioral compounds that respond to environmental cues and modulate the muscle control signals it sends. Heat, lower. Dry air, lower. Wrong vibration, different direction. The ant's body is the probe. The fungus's chemistry is the navigation system. When the conditions match, the chemistry locks. The ant stops moving. The mandible muscles receive a final compound that causes them to seize closed and stay closed. This is called the death grip. Her jaws are now biting into the main vein of the leaf. She tries to release them. She cannot. Carpenter ants can release a bite normally. It is a routine motor function. Her brain is sending the signal. The muscles are not responding. The Penn State research describes a final compound the fungus releases that causes atrophy of the muscles around the mandible joint, locking them physically into the closed position. There is no muscular pathway back. The bite is permanent. She will remain alive in this position for several more hours. The ant dies somewhere between 4 and 10 days after the initial infection. The fungus had nothing personal against her, it just needed her body to be in a specific location, in a specific posture, with a specific grip strength on a specific leaf vein. Now it begins the next phase. The fungus consumes the rest of the ant from the inside. Within 7 days of her death, a dark stroma, a stalk, pushes its way out of the back of her head. It grows slowly, sometimes for weeks. It eventually develops a flask-shaped fruiting body called parathecia, which is the structure that releases the next generation of spores. The whole process, from infection to spore release, takes roughly 2 to 3 weeks. The full development of the fruiting body, however, can take 3 months or more. When the parathecia mature, they release spores by the thousand. The spores fall in a column, downward, toward whatever surface is below. Most will land on dead leaves. Some will land on damp soil. A few will land on other species of insects they cannot infect. And 1 or 2 of them, given enough spores per host and enough host density per forest, will land on a Camponotus leonardi, the right ant. The 2 stories converge here, on the underside of a leaf 26 centimeters above the rainforest floor. The ant did not know she was being used as a vehicle. Her brain was not invaded. Her sisters in the colony never detected anything wrong. They continued to feed her until the day she left the colony for the last time. They did not stop her from leaving. The fungus did not have a brain, a will, or an intention. It had chemistry. The chemistry worked. This relationship has existed for about 48 million years. Both species are still here. If you watched this to the end, hit subscribe. Next week, the parasite that becomes a tongue.